Okay, this is 1.6. Our objective from the last slide that I already went through was to use trig functions to model periodic behavior and applications. Here we have even and odd trig functions. We see that cosine and secant, the reciprocal of cosine, are even functions and symmetric with the y-axis. And then every other trig function is going to be odd. This one says show that cosine is an even function and that sine's an odd function. Every year when I teach this in trig pre-calc, I have kids who have this exact problem, because this is a trig pre-calc problem that writes, you told us, or this is the formula you told us, or whatever. It's always something like, you said it, so it's true. Well, there's other ways to show that. Obviously, I'm telling you guys the truth here, but that's not the way we're going to show it mathematically. We already showed things that were even and odd, and we did the even by replacing. Let's do this. Give me 1 second. Even. We take theta. We're showing that f of theta equals f of negative theta. So that is where we're trying to show, or what we're trying to show. We're going to use the fact that we have cosine of negative theta. And then when we look at the restricted domain of cosine, our restricted domain, I'm going to write just capital D, is 0 to pi. So that is the top half of our unit circle. If you look at the top half of the unit circle, it is always a y value that is positive. So we're going to relate it, and I'm going to give you these exactly in a few minutes, but we're going to relate it as adjacent, which is our x value, over our radius. So again, if you were looking at the unit circle, I don't know how much of this you guys did last year. Okay? We're here, we have an angle. Let me do this in a different color. So this is just to visualize what we're seeing. You don't necessarily have to write it. You have your theta. We have our x value, our y value, and our r value. For it to be cosine, it's going to be the top half where our y is always, where am I at? Adjacent. Yeah, our x is positive and our y is positive. So we could have a negative x value on the other side. But we see that that is also representative, and we'll see this again in a second, of cosine theta. That is our formula for cosine theta. You see that it is that adjacent, and then over that radius, which is our hypotenuse. So we see that that's the same. Thank you, sir. Much appreciated. Let me grab your packet. And so therefore it is even. So we're going to prove that sine is odd. And here we're looking for f of negative theta equals negative f of theta. Let's try that again, Jenkins. There we go. Okay, so here we see that we would have sine of negative theta. For this one, we have, how do I want to say it? The formula for this, since it's sine, is going to be opposite y over hypotenuse r. And you see it there, and our restricted domain is from pi over 2 to negative pi over 2. I should say it, negative pi over 2 to pi over 2. So we would see here that that would make a negative y over r. And if you multiplied the formula for sine, and again, we'll go through all of these in terms of the unit circle. It should have came first. I just did not organize it that way in a few minutes, where I go through what each cosine, sine, tangent, cosecant, secant, cotangent look like in terms of y, r, and x. In case you don't remember, we'd see if we multiplied through, well, sine's traditionally just y over r. That would give you the exact same thing if you multiplied by that negative. So negative sine of theta. And I just have it on here for you guys to remind yourself if this is something you haven't done in a while. So we have sine of theta is opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse. Tangent of theta is opposite over adjacent. And then we go to cotangent. It's going to be the reciprocal of tangent, adjacent over opposite. Secant, the reciprocal of cosine, hypotenuse over adjacent. And cosecant, the reciprocal of sine, hypotenuse over opposite. Here's the slide that probably should come first. I made a note to change that for next year. So let P be the point XY on the circle with radius R. associated with the angle theta. Then we see that sine of theta is y over r, where r again is that hypotenuse. And then we have cosine of theta, x over r, tangent y over x, cotangent x over y, secant r over x, and then cosecant r over y. Starting here, we're just evaluating using the unit circle. I do not see any point at this semester that I'm going to take down the unit circle from my room at this moment. If I do, I'll tell you. If you're going to take the AP test, it is expected that you know the entire unit circle, you have it memorized, and you feel very comfortable with it. But if you're looking at it now, and we're going to evaluate sine of 5 pi over 3, what do we get? So sine chicken strips is your second number, the second coordinate. What do we get? Say it a little louder. Perfect. Thank you, sir. Negative square root of 3 over 2. And then the next one up, you see we have secant, which is going to be the same as 1 over cosine of 4 pi over 3. And what do we get there? 1 over, thank you, negative 1/2, which gives us that negative 2. So this is just making sure that you know how to look at the unit circle and evaluate from there. Number 4, find all the trigonometric values of theta if sine is negative 3 over 5. So remember here, with sine, I'm going to draw it like this. That's an ugly triangle. Let me try again. Okay? With sine, we have that opposite, which would be our negative 3 over our hypotenuse, which is 5. We knew that the 5 would be the positive because we always let that radius be the positive number. It'd be the x or the y coordinate that would be negative. We also see here that tangent of theta is less than 0, which means it's negative, which means only the x or the y is going to be negative, which allows us to know that this is going to be 4, based on the fact that tangent is negative. So only one of those numbers can be negative, which tells us that this is that 3-4-5 triangle, and the 4 has to be positive. After that, we just go through and we complete this. So sine of theta equals negative 3 over 5, cosine of theta 4 over 5, tangent of theta negative 3 over 4, and then we just do our reciprocals. Cosecant of theta negative 5 over 3, secant of theta 5 over 4, cotan of theta for negative 4. Let's try that again. I didn't leave enough space. Theta equals negative 4 over 3. So we're just going through. The only part here that was kind of tricky was making sure that you realized that 4 was going to be positive. I know you guys probably have some of these memorized, especially the ones that I have on the screen, but this is just going through the motions to show you if you got if you had to convert to radians of a number that you didn't know, degrees that you didn't know, you're just going to use that unit conversion that we have. So we have 30 degrees, and then we have to use the equivalent. So we have pi over 180 because that's the same as 1. We can then see how many times 30 goes into 180. We see that that's 6. This gives us pi over 6. Again, we know this, but we're verifying. We also have 45 degrees. Same conversion, pi over 180. We see here that 45 goes into 184 times, pi over 4. We have 60 times pi over 180. We see that 60 goes into 183 times. That gives me pi over 3. And we have 90 degrees times pi over 180 gives me pi over 2. Again, I know you probably knew these 4, but should you need it in the future, you at least have it. The other one here is going in the reverse. It's the same thing, but we flipped that in the our conversion fraction. So we have negative 5 pi over 6, and then we'll multiply by 180 divided by pi. Our pi's go away. And we see that 6 goes into here 30 times. 30 times negative 5 gives me a negative 150 degrees. I'm good with you leaving it as a negative 150 degrees, but if you wanted to get the positive, you could have added that 360, and that would have given you the positive coterminal angle. The next slide here is just us going through some of these identities. Again, I know you probably know the sine, the cosine, the cosine, the cotangent, the secant. But if you don't remember the Pythagorean identities, we have them there. Again, as long as you memorize the first one, sine squared plus cosine squared, bless you, equals 1, you can divide by sine squared, and you're going to get to the other one of the other ones. And if you divide by cosine squared, you'll get to the other one. So you can derive these if you want. Just make sure that you are keeping that in mind. These double and half angle formulas, these are ones that I don't necessarily have memorized myself. I keep on a sheet of paper or somewhere I can reference real quickly so I can come back to them. If you have them memorized, that's fantastic. But we will be using them. But make sure you have them somewhere handy is basically what I'm getting at. Okay, example 7. It says solve the square root of 2 sine x plus 1 equals 0. I'm going to write it out because I have that square root written in there. I just want you guys to be able to see what this looks like. So it equals the square root of 2 sine x plus 1 equals 0. So I want to be able to solve for our x. We can do this by subtracting 1. So I have square root of 2 sine x equals negative 1. I can then divide by my square root of 2. I get sine x equals the negative, rationalizing it, square root of 2 over 2. Then I'm going to look on the unit circle and see where this is true. So where do we see this to be true? Say it a little louder. 5 pi over 4 is what you said? And? Pi over 4? We're looking, I traditionally write plus or minus, but the fact that you say it's an integer would account for that. So if you would have just said plus, I would have been okay. But standard is we do traditionally put the plus or minus. Okay. Are you okay if I switch the slide? Any questions? Okay. A periodic function. A function f of x is periodic if there's a positive number p such that f of x plus p equals f of x. For every x value for every value of x, the smallest such value of p is the period of f of x, or of f. So here you see we have our periods written in here for sine, cosine, secant, cosecant. We see it's the 2 pi. And once again, for tangent and cotangent, it's pi. They're the only ones that are different. So transformation of trig functions, trigonometric functions, f of x equals a sine of 2 pi over b, which then times the quantity x minus c plus d. So here on your paper, I forgot that in bracket. You should add that in, as I added into mine. Again, the absolute value of a is your amplitude. The b you have to find by using that 2 pi over b here. C is your horizontal shift, and d is your vertical shift. Some of this is slightly different than regular transformations, but obviously some of it's very similar. Okay. So our first one here says determine the period, the domain, the range, and then draw the graph of the function y equals 3 cosine of 2x minus pi plus 1. I did this yesterday when I went through this slide with my other class. I'm going to go back one real quick. The important part for me to point out here, and I thought I would remember, is that it is x with a coefficient of 1 inside those parentheses. That is standard form. So when we're on this next slide, we need to make sure that we are meeting that standard form. So we are going to factor out the 2. So I have y equals 3 cosine, and then I have parentheses 2x minus pi over 2 plus 1. Okay, so for our period, for A, we're going to have to use the fact that we know that 2 pi over b equals our value right here, 2. So again, I'm just using that equation from before, setting it equal to the same spot, and solving from here. We see that that would give us b equals 2 pi over 2, which is equal to pi. So our period for this function is pi. This is still a cosine function, so what would our domain be? Exactly right. Negative infinity to positive infinity. I probably should have done something to show that was going to be the domain. And then our range. So here we see we have an amplitude of 3. So that means traditionally we'd be going up 3 and down 3. But the plus 1 moves it up 1. So now instead, we're going to join one more up here, and we don't need this one. So we see our range, C, is going to be -2 to 4. And then I just did a rough sketch. If you want to look at mine, you can. It's going to be a little rough. If you want to look at yours, you can. That's going to be fine too. I just did one to have the idea of what this is going to look like. You feel free to put it in your calculator. Okay. Not probably the best. Let me go a little bit further on both sides. I would like to make that look a little clearer. And then we can go here. And I'm going to do the same here. I don't know when I paused my video, so I'm just going to recap. We had our period. We did the 2 pi divided by b, and we set that equal to 2, the position that's in. We divided over by 2, so we see that b equals pi. We saw that the domain was from negative infinity to positive infinity, and our range, the traditional amplitude, was 3 to -3. The vertical shift brought us up 1, so that gave us the range of -2 to 4. And then we sketched a rough graph. Okay. Inverse sine and cosine. So y equals sine inverse of x is the value of y such that x equals sine of y, where y is between negative pi over 2 to pi over 2. And then we have cosine, y equals cosine inverse is the value of y such that x equals cosine y, where 0, or y is between 0 and pi. So here we have a table filled with the domain and ranges of our inverse trig functions. So just make sure that you feel comfortable with these. You notice here of our 3 main ones that our cosine's the one that's different. Okay, so we have sine inverse of 1/2. Again, sadness, I didn't put the annotate mode on, it went too far. Okay, now we're here. So we have sine inverse of 1/2. Again, I'm just writing it so you can see it in proper form. You don't necessarily have to rewrite it. And then we had to check to make sure that that 1/2 is in our domain of -1 to 1 of our sine inverse. So the domain of sine inverse is -1 to 1. It is, in fact, in the domain, so there we can evaluate. And then we had to remember we're looking for our range, or where it's the values that are going to be in our range, is how I should phrase that, which is going to be negative pi over 2 to pi over 2. So we are looking for where sine equals 1/2 on the right side of our unit circle. So on the unit circle, I have it written out for our traditional sine and cosine, but you would see that this value would be, let me make sure that I'm at the right spot and reading it correctly, 1/2. So we see that that would be at that 330, but we don't write it that way because that's not technically in the domain. So the way we would write this would be that negative pi over 6. So instead of writing it using the entire unit circle, we would do just the positive or negative values in reference to pi. Does that make sense? Next up, we have cosine inverse of cosine of pi over 4. First thing we have to do is evaluate the inside. We know that the cosine of pi over 4 is going to give us that square root of 2 over 2. I have to check to make sure it's in the domain. So our domain is going to be, for our cosine inverse, -1 to 1. It is, in fact, in the domain. If you put it into your calculator, you get 0.707106. So then we are going to look to see if it's in the range. Our range for their cosine range, I don't need to write the whole thing out. I can just do range. So range for this one, cosine inverse, is going to be from 0 to pi. So we're looking on the top half of our unit circle for where we have a cosine value of square root of 2 over 2. And we arrive at pi over 4. The next one is slightly different. Yep. So I started here because we're going to find the other two trig functions. Theta. So again, if we were going to write this out, it would be theta equals tan inverse of 3 over 4. If you wanted to see it the other way, like Xavier brought up, perfectly fine. Tan of theta equals 3 over 4. We know tangent to be opposite and adjacent, so we have 3, 4, and once again we see it's a 3, 4, 5 triangle. Pretty common for today's lesson. We have cosine, adjacent over hypotenuse. Adjacent is next to, hypotenuse is 5, and we have sine, opposite is 3, hypotenuse is 5. So sorry, can you say it one more time? Question. Example 12. Use right triangles to explain why cosine inverse of x plus sine inverse of x, that should say equals, that's a typo, equals pi over 2. Because if not, it doesn't make any sense. Okay, so for the purpose of this, I'm going to say we're going to let a equal sine inverse of x. Okay, so rewriting this, I can say that x equals sine of a. You could have picked cosine inverse. It would work the same way. I just picked sine inverse. So knowing that a equals sine inverse, where I have my sine inverse right here, I would like to highlight it right here. I can replace that with a. So I have a plus cosine inverse of x equals pi over 2. Our next step to get to the point we need to be, I'm going to substitute in, based on what we let our a be, we're going to substitute in for x. So now I'm going to take what I have for x right here and sub it in for my x right here. So we're going to do that in our next step. A plus cosine inverse of sine of a equals pi over 2. This requires me to remember an identity. If you do not remember this identity, it's perfectly fine. I have a handout I'm going to give you guys on it. But we can relate that the sine of a to cosine, because those two things, I'm going to write it off to the side here. We know that sine of a equals cosine of pi divided by 2 minus a. So that's an identity, and I'm going to switch that out. So I have a plus cosine inverse of, and then here I'm going to put in that cosine, pi over 2 minus a equals pi over 2. You see that I write like a giant, so I ran out of space quickly. I'm going to pick up right over here. That has us having a plus, and then you have cosine inverse of cosine. Those drop out and you're left with just what's left in the argument. Pi over 2 minus a equals pi. And then you see the beauty of this. We have a minus a. It shows us that pi over 2 equals pi over 2. Again, you could have done this with cosine. You would just have had to use the cosine identity down a little bit further, but it is possible to do it both ways. So, other inverse trigonometric functions. This was kind of covered in that other slide. So this is just it saying it again. You can look through it, but we already did this in the domain and range section. But it's just covered again. And then our last example is evaluate tan inverse of 1 over the square root of 2. So for me to evaluate this, or to find this, I could rewrite this as tan of theta equals 1 over the square root of 2. And I can create my nice little triangle. It's not beautiful, but it is what it is of theta. Tangent is opposite over adjacent. And I can solve for my hypotenuse. We're going to use that Pythagorean theorem. Square root of 1 squared plus the square root of 2 squared. And we see that gives me the square root of 3. I didn't have to go this far. It just says to evaluate. I just did all of this for really nothing. I can put it into my calculator. Tan inverse of 1 over the square root of 2. If you are in radians, what do you get? I asked, but I probably won't be able to hear you. So I'm going to give you a second to put it in to your calculator, see what you get. And then I'm going to have us do it in degrees as well. So I have 0.615 radians or rads. And if you change it to degrees, switch my mode. I have 35.264 degrees. And that's the end of this.